All right. Good morning, everyone. So I think we'll get started. Um, so a couple reminder items here. Homework 6 is due tomorrow. Okay. I do have office hours this afternoon and tomorrow morning. So if you need any help on your homework 6, let me know. We can set up a Zoom. Um, Also, the second reminder will be exam 2. Okay, so this coming Friday, we'll have our exam number 2. And again, we will have I will divide you guys into two groups. The Friday lab attendees, you will still meet in the normal classroom, region 14. For Wednesday lab attendees, we are going to meet again in faculty 108 as we did last time for exam 1. Okay, so that's on exam number 2. All right. So I think we'll get started on the lecture part, okay? So last time we talked about electric flux, and then this is the foundation for applying Gauss's law. For this part of lecture, again, it's not in the textbook, so if you want, you should write notes down on this lecture. Also, you can actually Google electric flux and Gauss's law. There should be plenty of references on this. Okay, so it's not difficult to find um, the content on this one online. Um, so for the electric flux, it's defined as the E times A times cosine theta. E is the electric field times the area times theta cosine theta, where theta is the normal direction of the surface makes with the electric field. Okay, so that's the theta there. So it's basically what's the electric field going through a certain area A. Okay, it has a SI unit of newtons times meters square over coulomb. Um, so if you have an enclosed surface, say if you have a sphere, right? So it's an enclosed surface. Then for the convention of the sign for flux, because you can imagine for a plane, you can have electric field going into the plane. You can have also it going out of the plane, right? So the convention is for the flux, it will be positive for the field line that leaves the enclosed volume of the surface, okay? If you have a sphere, if you have electric field going out of the sphere, then the flux is positive, okay? Now, flux is negative when the field lines are going into the volume, enter the volume. So then in that sense, if you have a sphere, if you have electric field going into it, then um, the flux to the spherical surface will be negative, okay? That's the convention for positive and negative flux. Let's take a look on this one. So if you have a point charge at the center of sphere, okay, so you can see that electric field lines are going out of the sphere and radius away from the point charge. So in that case, you can calculate what's the flux through this spherical. So imagine this is a three-dimensional sphere instead of circle, okay? Out of this sphere, field lines are going away. So your flux is equal to E times A. Now, cosine theta, the theta should be 0 at any given point because electric field line and then the normal direction of the surface at that particular point is in the same direction. So this is for a sphere. Normal direction should be from the center of the sphere and going out of it. Okay, so electric field lines and the normal direction of the surface, they are the same all the time. So flux is equal to E times A, okay, over here. And then for E, it's the electric field. We know that for point charge electric field is KQ over R squared, okay, times the area of the sphere. Area for sphere is 4 pi R squared, okay. So R squared and R squared will cancel out. Then you have K over or 4 pi times K times Q, all right? That would be your resultant flux. So there's a step missing here. Let me show you the full derivation over here. Um, so when we are doing So when we are doing the phi, the flux equal to E times A, that goes to KQ over R squared times 4 pi R squared, okay? And then R squared and R squared will cancel out, so you'll have 4 pi K times Q, all right? Now, so for the K here, all right, you can see K is related to epsilon naught. So epsilon naught is equal to 1 over 4 pi K, then K will be equal to, okay, in this case, will be equal to 1 over 4 pi epsilon naught. So basically, you are exchanging epsilon naught and K, okay? So if let's K, you take that expression over here, then this is equal to 4 pi times 1 over 4 pi epsilon naught times Q, okay? K is equal to that. So then 4 pi and 4 pi will go away. So then your flux, okay, from here will be just equal to Q over epsilon naught, okay? So this is for the electric flux, okay, through the sphere, which enclose a point charge at the center, all right? Now, sphere is a well-defined shape. If you have an arbitrary shape surface, okay, then things will be difficult to calculate for the flux. But however, it turns out that flux should be the same here. So flux, if you have different types of surface or volume that enclose this charge, then it will be still equal to Q over epsilon naught, okay? So that's basically Gauss's law. It says, oh, let me go back to the slides. I guess I forgot to reshare the slides there. Okay, so so then that's basically Gauss's law. It says the flux is equal to the charge enclosed divided by epsilon naught. Okay, epsilon naught has been a constant of 8.85 times 10 to the negative 12. So even if you have a sphere have irregular shape like that, as long as it encloses the charge, then the flux is equal to Q over epsilon naught. Okay, the charge enclosed. Okay, so this is basically Gauss's law. Now, you can see here we use Q instead of absolute value of Q. That's because for positive Q, electric field goes outward, okay, leaving the surface, so then you have positive flux. For a negative charge here, electric field will point inward, going into the body. So then you will have negative flux, okay? So then we just use Q because that will be consistent with the sign of the flux that you are getting, okay? All right, so you can calculate also flux is Gauss's law. All right, so that's a second way of calculating flux. The first way is to use the definition, flux is equal to E times A times cosine theta, okay? And then second way of calculating flux, you can use Gauss's law, flux equals to charge enclosed divided by epsilon naught, where epsilon naught is the constant. All right, so then let's take a look on a few applications of Gauss's law. The first one we are going to look at is to look at the application of Gauss's law to an infinity line charge, charge distribution. Okay, so if you have the charge on this green line, where this green line is infinitely long, so then what would be the electric field, say a distance r away from this line? Okay, so let's take a look here. And it tells you that this line has charge density of lambda. Okay, so if you see lambda, that means charge density per unit length. Okay, so this linear charge density. All right, and then we will take a look on the other charge density as well, the surface charge density distribution, and then also the volume charge distribution. Okay, later on. But let's take a look on this one here. So the first thing, let me just draw the figure here on the paper, and then I'm going to just stop sharing here so you can see a better view on the figure. All right. So first thing, you want to draw a line. This is infinity long line, okay? So then if say you are a distance r away, so we are going to take a distance r away. This is your point of interest, okay? Where is r away from here? Now let's analyze and to see what will be the electric field, the direction of electric field at this point, okay? So let's take a small portion of the line from here, okay? So then let's say that's delta Q, okay? So we can treat this small portion of delta Q as a point charge, okay? So then this point charge will produce an electric field at this point of interest P, okay? In this direction, that will be the E field, all right? That will be the delta E that this guy generated, right? And now, because this is an infinity long line, so you can always find another small portion of the line that carries the same charge delta Q, right? So delta Q on this side here, which is equal distance away from here, this point, center point over here, okay? So then this guy will generate of another delta E, right, in this direction, all right? So that's on that, in that direction, this guy is in this direction. Okay, now you can see because these two are the same charge, so the magnitude they generate at this point P, where this R and then the R distance is the same, should be having the same magnitude, right? Now, in the direction that is parallel to the line charge, okay, you can see component of this guy over here will cancel out component of this guy, right? Because one points in one direction, the other one points in the other direction. So this guy will cancel out that guy, right? So in this direction, the electric field will cancel out by those two charges. Then in this direction, the components of these two electric field will add up because they are pointing in the same direction, right? So we can see that electric field at a particular point P that is R away should be in the direction that is perpendicular to the line and then pointing away, right? So that would be the E field over there overall. It will be similar on this end. If you are distance r away here, then electric field will be pointing away, similar for the similar reason. So E field will be in this direction, okay? If you are above the page over here, then it's pointing outward, okay? So basically, electric field that is distance r away from the line, it's pointing outward in all directions, okay? That is perpendicular to the line, okay? So in that sense, then we can pick a volume. So in this case, we'll pick a cylindrical volume, okay? A cylinder, okay? That has a radius of r, and the line charge distribution goes through the center axis of this cylinder, okay? So then the surface of this volume, cylinder volume, cylindrical volume, this base area, and then the side area over here, okay, the side here, that encloses a line. So let's say this cylinder is L in length, okay, and then radius of R, okay. So we can calculate then the flux through the enclosed surface of this cylinder. So that means the surface area of this cylinder, the two bottom sides plus the side surface there, okay. So flux can be equal to on this bottom side and that bottom side, because electric field is perpendicular to this line. So then electric field is parallel to this bottom side and that bottom side, right? So it should be 0 plus 0. So that's this guy, and then the other 0 is that guy, okay? Plus the side surface times the electric field E, all right? Times the side surface would be the circumference of the base, 2 pi r times L, okay? So this is A, the area of the side. So then flux is equal to this. Okay, so this is by doing EA cosine theta. Okay, and then because you have three surfaces, then you add the three surfaces up. Okay, now you can also apply Gauss's law, where it says phi is equal to Q enclosed by this volume divided by epsilon naught. Okay, and then the Q should be, because this line the portion of the line is enclosed by the volume will be length L. Okay, so Q will be then lambda, the line charge density times the length over epsilon naught. Okay, so then this is by Gauss's law here. Okay, now you have both. You have the flux calculated in two ways, and then the flux should be equal to each other, right? So then you can set this equal to that. So your E times 2 pi times R times L is equal to lambda times L over epsilon naught. Okay, so you can see L and L will cancel out. So then E field is equal to lambda over 2 pi. Okay, 2 pi is a constant, epsilon naught is a constant, R is the distance away from that wire. So that's will give you the magnitude for the electric field is equal to lambda over 2 pi epsilon naught times R. Okay, so that's the electric field, and then it's radially away, okay, from the line. All right. Any questions you guys might have? So electric field for a long line, an infinity long line of charge distribution should be equal to the linear charge density of the line divided by 2 pi epsilon naught times R, where this is the distance of your point of interest from the line. Okay. All right. So if you are clear, we can move on then. The second application will be looking at the Gauss's law that you can apply to calculate the electric field for a sheet of charge distribution. So this is an aerial charge distribution. Okay, so what if this sheet is large? Okay, and the charge distribution is uniform. Okay, so let's take a look here. Again, the first thing you want to determine is what will be the direction of the electric field out of infinity large sheet. Okay, so let's take a look here. Now I'm going to assume this is the sheet of charge distribution. Okay, and then I'm going to just assuming we are distance r away from the sheet above it. Okay, so this is r, distance r away. Now this is our point of interest P. Now for infinity large sheet, we are going to pick a small patch out of the sheet, okay, where this patch carries delta Q. So similarly here, we can treat this patch as a point charge. It will produce an electric field at this point P, delta E in that direction, okay. Now, because this is a infinity large sheet, you can pick at a distance, the same distance over here on the sheet over here. All right, and then again, the same delta Q here, you can pick that way. So then this guy will produce a delta E at this point of interest. Okay, delta E over there. So you can see similarly parallel to the sheet in that direction, component of delta E here will cancel out component of delta E in the opposite direction. Okay, and then in the direction perpendicular to the sheet, the two components will add up. All right, so then your E field will be just in this direction, perpendicular to the sheet. Okay, pointing away from it if this is positively charged. All right, similarly, on the other end, on the other side of the sheet, if you are distance r away, then you will also expect the electric field is in that direction perpendicular to the sheet but pointing away. Okay, so then again, we kind of analyze the scenario, and then we can determine the electric field should be pointing away from the sheet. Okay. So in that case, now let's take a look on the problem we have here. So we are having a sheet, something like this, and then it carries charge, which is this uniformly distributed through the area here of sigma. Okay, so sigma is equal to the total charge over the area. All right. Again, we are going to pick a cylindrical volume. All right, that has a base having the radius of r. Okay, like this, and then we are going to extend it backward to the other end. All right, so the two bases are equal distance away. All right, so let's say, or in this case, let's say this is L, distance L, or let's rather call it half L. All right, so let's call this half L. And then on the other side, you have also half L, okay, for the length. And then the radius of the base is R, okay. So we can calculate again flux by using E times A cosine theta. Again, in this case, your this is the surface that you are looking at. So there are two base surfaces here, and then there are side surface. Okay. So for the two base surface, this would be equal to flux would be equal to E times A in this case. Okay, so E field is pointing away, and then the E is perpendicular to the surface. So then E and A, the normal direction of surface are in the same direction. So E times A. And then you have two bases, so 2 times E times A. Okay, and plus for the side. For the side here, now the side is side surface is parallel to your E field, right? Because your E field is perpendicular to the sheet. Your side is also perpendicular to the sheet. So that should be 0, okay? So this is 2 times of E times the area pi r squared. This is your flux. Calculating from the definition of flux. Also, you can calculate your flux from Gauss's law equal to Q over epsilon naught, okay? So in this Q will be equal to the surface charge density distribution times area, okay, over epsilon naught. So this is sigma pi r squared over epsilon naught. And flux calculated from two methods should be equal to each other. So you set this equal to that, okay? Twice of E pi r squared is equal to sigma times pi r squared over epsilon naught. Okay. The pi r squared and pi r squared will cancel out. All right. So then E field will be just equal to sigma over twice of epsilon naught. Okay. So for an infinity large sheet, your E field is equal to sigma divided by 2 times epsilon naught, the constant number. So it doesn't have a distance r in it. So that means for an infinitely surface charge distribution, your E field is independent of the distance away from the sheet. Okay, so E is equal to surface density, charge density over 2 times epsilon naught. All right. Questions you guys might have? You can unmute yourself and speak up, or you can type in your question in the chat, okay? All right. If not, we'll move on here. So remember a couple of weeks ago when we just started the chapter, we say for parallel plate capacitor, it's capacitance is equal to epsilon 0 times A divided by D, right? And then we didn't really derive this equation, okay? So today we are going to just see how this equation is being derived. After that, we have learned that for a surface charge, the electric field on the side will be equal to sigma divided by 2 pi epsilon naught, okay? So let's take a look here. If you have a parallel plate capacitor, so this is what you have. You have one sheet on one side. So this one is positively charged. You have a second sheet that is on the other side, which is negatively charged, okay? Now, let's assume this is sigma, all right? The surface charge is sigma, which is equal to Q over A, the area of the plate, right? On this other side is should be minus sigma, okay, which is negative Q over A. So then electric field here by this plate, right, will be equal to, according to what we just derived, it will be equal to sigma over 2 epsilon, right? So then in this case, electric field in between here will be equal to, this guy will be equal to sigma over 2 epsilon naught, right? By the other plate, negative plate, then it will be pointing towards that, right? Also sigma over 2 epsilon naught, okay? So then in between two plates, you would have these two add up, right? So then E field will be equal to sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which means sigma over 2 epsilon naught multiplied by 2, which is sigma over epsilon naught. Okay, so this is the E field. Now, for capacitance, it's defined as Q over V, right? So we have the Q, which is this here. So Q could be, Q is equal to sigma times A, all right? Now V for the volume of this is the electric potential across the two plates. That should be equal to the E field times the distance or the separation of the two plates, okay? So then this would be equal to E would be equal to sigma over epsilon naught times D, all right? So you can see then C should equal to Q, which is sigma times A over V, which is sigma times D over epsilon naught, okay? So then you can see sigma and sigma will cancel out. Then epsilon naught down here should go up there. So this is equal to epsilon naught times A over D, okay? And this is what we have on the slide for the capacitance of the parallel plate capacitors, okay? So capacitance equal to epsilon naught times A over D, okay? Where epsilon naught is the constant of 8.85 times 10 to the negative 12. All right. Okay, so that's Gauss's law applied to surface charge distribution. Okay, now the last application of Gauss's law we will be looking at is Gauss's law applied to a volume charge distribution. Okay, so let's say if you have a sphere that has a radius of capital R, all right, has charge uniformly distributed through the volume here. So then in this case, you can use rho as the charge density per unit volume. Okay. So the question would be, what would be the electric field inside the volume and then also outside the volume here? Okay, distance r away. So in the first case, your r is less or equal to the radius capital R. In the second case, your radius small r is greater than capital R. Okay. So in this case, we can also derive We can also write flux from two ways. The first is calculating flux by definition. So E times A times cosine theta, okay? Now, for a volume distribution, if you take starting from the center of volume, so you can expect that the electric field is going outward, okay? So E will be in that direction, and then normal direction will be in the same direction. So it should be the same of E times A. For the charge enclosed row, if you calculate flux from Gauss's law, so in this case, your total charge should be just for the spherical volume of this small sphere, okay, not the total layer. So you would just include part of the charge. In the other case, you will include all, okay, because the whole sphere is enclosed by that spherical volume, okay. So let's take a look here. If you are inside the sphere, R smaller or equal to capital R, okay, so inside. Your flux can be calculated by using E times area, where E is what you are looking for, so just write it down as that. For the area should be the spherical area, so 4 pi R squared, okay? From Gauss's law, you can calculate Q equals to flux, sorry, phi. Flux phi, okay, phi equals that. Phi equals to Q enclosed divided by epsilon naught. So in this case, for the enclosed, you will be using the, let's use the rho here, okay, rho times the small volume of the sphere. So 4/3 pi r to the q, okay, divided by epsilon naught. These two should be equal to other again, okay? So then you can set it up, E times 4 pi r squared equals to rho times 4/3 pi r to the q over epsilon naught. So 4 pi r squared here will cancel out 4 pi and r squared. So with just r remaining, okay? So rho times r over 3. So E is equal to rho times r over 3 epsilon naught, okay? So this is for when you are inside the sphere, okay? For r small or less than r. All right. Now, if you are outside the sphere, your small r is greater than the radius of the sphere, so outside. You can do the same. The flux can be calculated as E times A, which is E times 4 pi r squared, right? You can calculate flux from Gauss's law, Q enclosed over epsilon naught. Q enclosed this time rho will be rho times 4/3 pi, just capital R to the Q over epsilon naught. Okay, so the volume of the sphere. In this case, you are outside, so you can include all the charges on this spherical distribution charge. Okay. Again, these two should be equal to each other, so you can set up E times 4 pi small r squared equals to rho times 4/3 pi capital R to the Q over epsilon naught. Okay. Now you see that this 4 pi here can cancel out this 4 and pi, but this is small r, this is capital R. They do not cancel out. Okay, you would move this guy down there. So then E will be equal to rho times R to the Q over 3 epsilon naught. All right, times R squared. Okay. So if you are outside, so this is for R is greater than R. If you are outside the sphere, okay, that's your E field. So for these two expressions, you can see that electric field inside the sphere will be proportional to the radius, okay? R, your point of interest, away from the center of the sphere. For electric field outside of the sphere, it's going to be inversely proportional to the distance away from the center of sphere. Okay, so over r squared, 1 over r squared. Okay. or actually it should be by this slice over here. So if you plot the E field that is r distance away, you can see inside the sphere, inside smaller than r, it goes up linearly as distance r, and then inversely proportional to r squared outside the sphere. Okay, so this is what you get. All right. All right, now let's take a look one example. If you guys don't have a question about that derivation on the previous slide, let me know if you have any question, okay? Otherwise, let's take a look on this example. It says a non-conducting sphere of radius 6.0 centimeter has a uniform volume charge distribution of 450 newtons nanocoulombs over meters cubed. It asks you to find the electric field at the following distance from the sphere center. First one at 2 centimeters away from the center of the sphere. The second one 10 centimeters away. Okay, so the first one is inside the sphere. The second one should be outside the sphere. Okay, so you can go ahead and then calculate those two. All right, I'll give you guys a few minutes to work on this, and then we can take a look on the solution together after that. So I have my microphone muted. Okay. Um, so let's take a look here. So as I said, this is what you get earlier. So pretty much this is what you are going to apply. You are going to calculate flux from definition, which is E times 4 pi r square. You are going to calculate flux from Gauss's law. This is inside the sphere. So you'll end up with this expression E inside the sphere is rho r over 3 epsilon naught. Okay, so basically here, then I kind of did this quickly again. So this is your charge distribution. Now you take a small radius r here for the sphere. So this is a spherical volume here that encloses the charge. Okay, so this is only this part that in red that will count as your Q enclosed. Okay, so if you see in a textbook or in a problem, it says Gaussian surface. So basically that means the surface you use to apply Gauss's law. Okay, so that will be the surface have a charge enclose it. Okay, and then you apply Gauss's law by using that surface. Okay. So again, by definition, E times area will be equal to the charge enclosed divided by the epsilon naught. So then E field will be equal to Q enclosed over 4 pi r squared epsilon naught. Basically, move this term down there. All right. For Q enclosed should be rho times the volumes, 4 over 3 pi to the r to the Q. So 4 pi r squared will cancel out. You still have 1 r on top. So rho r over 3 epsilon naught, which is exactly what we got earlier. Okay. So at that point, you can apply, you can plug in the numbers here, given that rho is as 450 nano, so times 10 to the negative 9, and then radius as 2 centimeters, 2.00 times 10 to the minus 2 meters, okay? Over 3 times 8.85 times 10 to the negative 12 farad per meter. So this will give you 339 newtons over meter, okay, for the electric field at that point. All right. Now part B, you are outside of the sphere, so you can apply E, or you can do like E again, calculating E times 4 pi r squared, that should be equal to Q enclosed over epsilon naught. So this is Gauss's law. And then this is equal to rho 4 over 3 pi, this time just capital R to the Q, okay, over epsilon naught. That's your E of 4 pi r squared. Okay, so 4 pi and 4 pi will cancel out. And then this guy, you will move it to the other side. So then your E field is equal to rho capital R to the Q. You have 3 epsilon naught times R squared at the bottom here. Okay. Now you can plug in the numbers. You are given 450 times 10 to the negative 9 coulombs times R given as 6, okay, times 10 to the minus 2 meters to the Q over 3 times 8.85 times 10 to the negative 12 times small r, this time is 10, right? You are 10 times 10 to the negative 2 meters squared. All right. So your E field this time will be 366. All right, when you are away. So that's when you are outside of the sphere, okay? Let me know if you have questions on this one. All right, again, so if you have a spherical charge distribution, inside the sphere, electric field goes up proportionally to the distance r from the center, and then outside the sphere, it goes down inversely proportional to the distance r squared, okay? All right, so For another example here, so this one says, find the electric field due to uniformly charged thin spherical shell of radius r and total charge q. Okay. So in this case, if you are outside of the sphere of the shell, then you'll be getting about the same result as the spherical charge distribution, right? So it will be, so then the blue spherical area will be the Gaussian surface you have, all right? So in this case, we can take a look again. So outside the shell, when you are having R greater than capital R, so you have a shell here. Now charge is only on the surface of the shell because this is the shell, okay? Inside you have no charge. So then this is your Gaussian surface outside of it, okay? So this is R away, this is capital R. Your phi will be equal to, again, E times A will be E times 4 pi R square, okay? And then from Gauss's law, this will be equal to Q enclosed over epsilon naught, okay? So yeah, that's just it, Q. I think it just tells us Q. So this is capital Q over epsilon naught. So these two should be equal to each other again, okay? Because you calculate the same flux with two different methods. So then you can set up E times 4 pi R squared equals to Q over epsilon naught. All right, so then your E field will be equal to Q over 4 pi epsilon naught times R squared. Okay, this is when you are outside of the shell. Okay, you can put that equal sign. Just on the shell, it will be the same, like that. Okay, now inside the shell, so inside the shell, if you draw a Gaussian surface, okay, so then this volume, spherical volume, does not enclose any charge because charge is on the shell. Okay, you are inside the shell, so it doesn't enclose any Q. So then your E times A equals to, again, your phi from definition equal to E times A equals to E times 4 pi R squared. Okay, now from Gauss's law will be equal to 0 over epsilon naught. Okay, which is 0, right? Then you set the two equal to each other. So then basically it tells you E times 4 pi R squared is equal to 0. All right. So then your E should be equal to 0. So this is when you are inside. Okay. When you are inside the shell, this is what you get. All right. And if you plot it this time inside the shell, your E field is equal to 0. If you're outside the shell, it's similar to like 1 over R squared, exponential the decay like this 1 over R squared. Okay. All right. Now, if I ask you, so in the previous example, you can see here, it says a non-conducting sphere, right? What happens to a conducting sphere? Now, a conducting sphere, as we mentioned, like it's a conductor, right? So then the charge will not be inside the conductor, right? Inside the conductor, charge should be 0. So all the charge should be on the outside of the conductor. So then in that case, if you are inside the conductor, we know that inside the conductor also E field is equal to 0. Okay, so that's basically because inside the conductor, if you would draw a Gaussian surface, it will enclose 0 charge. So then electric field will be 0. Okay, you can explain it in the other way of using Gaussian's law like that. Okay. All right. Any questions you guys might have on Gauss's law? All right. So if not, I'm going to stop here for today, but just remind you guys, some of you guys were late today, but so homework 6 will be due tomorrow by midnight, okay? And then we'll have exam 2 on Friday. For lab attendees, Friday, you guys are in region 14, the classroom, the lab room. For you guys attending the lab on Wednesdays, we'll be meeting in faculty 108 as we did last time, okay? So that will be it for today's lecture, okay? I'll see you guys on Friday, all right? Bye, guys.